Those health gadgets we wear can reveal some of what's going on inside of us. The search is on to find ways to make them smaller and smarter. Forget about earthquakes and hurricanes. Some cities are heading for a slow motion disaster, and one researcher can show you why we're probably not prepared. And try to imagine modern life without concrete. It's durable but dirty to make. Can we make it cleaner without making it weaker? That's coming up next on Catalyst. This YouTube edition of Catalyst is brought to you by Arizona PBS and Arizona State University. Life has problems. Science turns them into questions that can lead to solutions and even innovations. This is Catalyst, shaping the future through science research at Arizona State University. Do you use your phone or one of those fitness trackers to make sure you're staying healthy and active? Those gadgets would be much more helpful if they could tell us more than just how many steps we're taking or how fast our hearts are beating. Researchers at Arizona State University are working to make trackers that are much more precise and useful. Wearable devices that might be able to diagnose a health problem even before the person wearing it knows something is wrong.
All of a sudden I started sweating, I had the left arm pain, which would normally be symptoms of a heart attack. One of the doctors came in and explained to me how I was going to go to the cath lab and they were going to take a look. And I don't remember anything after that except for the fact that I woke up some 20 days later in ICU. I had had 6 bypasses and that had left significant damage, enough that I had heart failure. One of the things about heart failure is it has a really bad name. And heart failure just means that your heart isn't pumping enough blood. So instead of working at full steam, my heart doesn't pump as much blood as forcefully as it needs to.
1 out of every 50 people in the developed world suffer from heart failure. It's a chronic condition that creates billions of dollars in medical costs in the US alone. If patients could continuously monitor their hearts and other vital signs, doctors could solve problems sooner.
When people's heart failure is starting to get a little bit worse, a few things happen. They may move a little slower. Their heart rate may go up when they're just sitting, or may go up quite a lot when they're doing a little bit of activity. So if we can monitor those things, we can sometimes catch signs that the heart failure is about to get worse before the person even knows that they feel bad.
Dr. Jeffrey LaBelle's lab engineers low-cost, wearable biosensors. Patients can wear these devices in everyday life. Several different types of sensors collect data continuously. They create information that doctors can use to diagnose disease.
What we're after is basically, if you've ever been in a hospital in an ICU unit and hooked up to a heart rate monitor and temperature sensors and other things like that, we're trying to take that technology and render it all down to a little wearable that you could have on your chest, and it could monitor you 24/7.
24/7 monitoring is a big benefit of wearable health monitors. In heart failure, symptoms can appear and disappear without warning. So a device that's on the body full-time could catch those changes at any time of day, no matter what the patient is doing.
For me, it was put a device on the patient and that's it. That's all they have to worry about at that point. One device, one time. If we can make the battery last 30 days, awesome. We get that data flow going without them doing anything, awesome. A lot of the current devices can't do that. A lot of the current devices will actually measure one parameter with one sensor and calculate the rest of the data for other parameters. So for example, you could take in an EKG, get heart rate from that, beat per minute. You could also estimate what a blood pressure would be. You could estimate what stress levels are. You could do lots of estimatations. But the second that device stops to fail or some garbage gets underneath the sensor, you have garbage for data. All the calculations go to pot. So we've been trying to integrate a lot of different sensors onto the same device so it's all orthogonal, or for one parameter, there's one sensor. Very few things are calculated. So what we are working on is breaking apart the electronics into different components, different sensors and different parts of the honeycomb, brains in the middle, and then maybe respiration, EKG, surface temperature, and other devices all out on the spokes of the honeycomb. And that way we have a more flexible wearable sensor using polymers that are very, very elastic, a lot more comfortable to wear. One of the little challenges is keeping the device waterproof, so a person could wear this while they're in a shower. A lot of the devices that are off in the market right now, if they're wearing these devices, okay, great, I gotta go take a shower. Off comes the device, they go in the shower, something happens. Or they come out of the shower and forgot about it, didn't put it back on. So we're trying to make wearability one of our chief features. The other reason for the honeycomb is even if we had rigid components, they're far enough away from each other that they'd be flexible just by design. But we're trying to isolate them from each other just because of noise. Or on the case of some of our readings, we need 2 electrodes on the person. We need them far enough apart. But I don't want to have multiple devices on them, so by moving them further away from each other, but it's all on one device, the person still only puts on one device.
But in order to get government approval, the newer devices will have to show they work at least as well as the bigger and bulkier ones.
What we're doing with this project is we are validating how well that honeycomb-looking device works against other sort of gold standard medical monitoring devices. So when you saw her hooked up to all of those wires, those are the gold standard devices. The reason that we do that is we want to make sure that when we put our honeycomb device on a subject or on a patient, that we know that it's going to work with very high accuracy. So we compare it to other devices that we know are very accurate. When we have an FDA approved device, we have confidence that that device is super accurate and is going to work super well and be really safe for the patient. And so we're committed to going through those steps, but we have to do our early testing here first.
But what about the gadgets like the Apple Watch or the Fitbit? Are these useful for patients with chronic diseases?
One of the things that we've learned from our research in the past 3 to 4 years through Project Honeybee is that those consumer grade devices, they're not very accurate. So they're great for helping you, motivate yourself to exercise, but they're not accurate enough to use for helping people manage chronic diseases.
I would love a better monitoring device. Pacemakers can monitor certain things about your heart and the rhythm, but we just don't have anything that people can easily point to and have that record, and that would so help other patients.
We're always going to the mechanic saying, my car's making a funny noise, but your car comes in perfectly fine. Mechanic can't figure out what's wrong with it. Same problem we have in healthcare. So, watching people all day, we can get a lot more information. We'll learn a lot more about our bodies by, wearing these devices.
When power plants burn coal, the process produces coal ash, and one of its byproducts is fly ash. It's a very fine powder that industry depends on to make concrete. For decades, companies have used fly ash to save money and to improve the strength of concrete. But with alternative energies on the rise and coal production on the decline, somebody needs to come up with a way to replace fly ash. One Arizona State University engineering lab is tackling this problem.
Coal ash is already a waste product. You have created the energy from burning coal, and this is the ash that flies out of the power plant, and then you capture it back and dump it in a landfill. You normally don't do anything with it. But what we have found out, and what people have done for what we know for 20-30 years now, is that this coal ash contains a lot of silica and alumina in it. So when you make them react, they are doing what cement originally used to do.
The fly ash gets introduced into the silo, cement on this one, and then it gets loaded depending on if the mix design calls for that fly ash or not.
In the western United States, Cal Portland Cement is a big player in concrete production. With more than 50 facilities spanning from Washington to Arizona, fly ash is one of their main ingredients.
So we use over 200 tons a day of fly ash on a daily basis for the Phoenix market. Fly ash by itself with water doesn't have any cementing properties, but when mixed with cement and water, it actually creates extra crystals and actually creates strength for concrete. If you look at it under a microscope, it's a sphere, so it actually acts like a lubricant in concrete, so it's easier to pump in high-rise buildings. When you have fly ash, it's easier to finish, to get a good smooth finish.
You're looking at concrete, if you're putting in such vast quantities, you're looking at concrete being a big contributor to greenhouse gas emissions. We need infrastructure, we need bridges, we need roads, so you're not going to control the amount of concrete that we have to use. So the only way is to control the amount of cement that goes into concrete. The more cement you have to use, the more limestone needs to be burned. The more limestone that you need to burn, more carbon dioxide gets emitted to the atmosphere. So our idea is to control the amount of limestone that needs to be burned to create cement that we use in all construction.
In other words, if cement companies use fly ash, less cement is needed in concrete, meaning reduced emissions from cement mines, something the Portland Cement Association says they've strived to do for the past 40 years.
A lot of these projects depend on the use of fly ash, and we have applications where they require sometimes fly ash. If we don't have the fly ash available, then that may delay projects.
For many years, Cal Portland and its competitors have relied heavily on fly ash. But as the production of coal drops, the availability of this ash is in question.
Because of the alternative energies that are available now, wind, solar, the demand for energy from coal power plants has diminished. Some of these coal power plants don't run throughout the whole year like they normally do, and there's seasonal shutdowns, so that affects us as a consumer.
The goal? Building stronger concrete while reducing its impact on the environment. Both ASU engineers and concrete companies are confronting this issue.
Can we use other sort of materials in replacement of cement, Portland cement, to make it more sustainable, but at the same time not sacrifice any strength, not sacrifice any of those material properties that we want in a sound, strong structure?
So what I have here is a small sample of concrete. So what I'm going to do is take my concrete and put it in my microscope. This is the surface on the micro scale of this piece of concrete right now. And I can also determine the forces acting on the surface of the concrete, because the forces acting on the micro scale are ultimately what's responsible for the macro big properties of concrete.
So we look at right from the atomic structure, right? We look at very, very, very closely all the way down to the smallest scale that you can see, and see how these structures are organized at that level, so that we can understand if there is some relationship with that to the bulk scale performance.
And what's happening is these two cameras are taking pictures once every second. And with this algorithm and software, it's able to track where those speckles are moving and give us exactly where the crack is happening.
At the end of the day, it's not just enough to replace Portland cement. The structure has to stand, the structure has to perform, and the structure has to be maintenance-free for a certain period of time.
Fly ash has long been the favorite solution, but its future is in doubt. So what is the next step?
Since we got used to it, it's going to be hard to kind of see it go away, but that's kind of out of our control in a sense.
People will have to start looking elsewhere, for that refinement of the pore structure, for that increased durability, and for that extended service life. And that's where other materials come in. What I have here is, 5 different powders. We have irregular Portland cement, fly ash. We have silica fume, metakaolin, limestone. So again, whenever you think about sustainability, it's environmentally friendly to use materials that aren't environmentally damaging like Portland cement, but at the same time, you have to make sure you're using them effectively.
There hasn't been an economical solution to replacing the Portland cement. It is still a product that gets used every day, and it's the most widely used construction product. So trying to replace that with something that's going to be more cost effective, I don't think we're there yet.
Anytime you have concrete in the infrastructure like bridges and roads and dams and nuclear reactors, the point is that you're building these structures for 50 or 60 years. And we don't have the performance of these materials that we are developing now without Portland cement established for that period of time. We have laboratory results, we have limited results here and there that shows it's a good idea, but we don't have enough data to prove it to to a large customer like a Department of Transportation who puts in roads and bridges to show it's a good idea yet. But we'll get there.
As a driver in Arizona, you've likely been stuck in traffic, and while congestion is bad at times, it's not as gridlocked as Los Angeles yet. And a researcher at Arizona State University is worried that Phoenix may soon have the same traffic issues as LA, and he can show you why.
Phoenix in many ways is building a very automobile-centric infrastructure. Most of the transportation infrastructure that we're building tends to support automobile travel. And while we are building new light rail lines and we are adding biking and walking infrastructure, for the most part what we're seeing is an automobile-focused paradigm. So Los Angeles largely grew as well around the automobile, built itself into congestion, and at the same time their infrastructure matured. So they've reached a point today where a lot of their infrastructure is basically at maturation, meaning that they can't add more of it, they can't add more roadway miles or widening of roads. So when we look at Los Angeles and we look at where it is roughly 30, 40 years after it started initially developing, we ask ourselves, is Phoenix on a similar path, on a similar trajectory? And there's a lot of evidence to suggest that that is the case.
Dr. Mikhail Chester studies city infrastructure to determine how traffic occurs and the significance of adding more roadways.
We are on the 101 South, headed towards downtown Los Angeles. It's about 12:30 on a weekday, and we are in bumper-to-bumper traffic. So in Phoenix, during the off-peak times, what you tend to see is not all that much bumper-to-bumper traffic on the freeways and even on many of the major arterials around the city. It tends to be a lot quieter. Whereas in LA, we tend to continue to see that bumper-to-bumper traffic even when we're in the off-peak times.
Chester says drivers in LA spend about 95% of their driving time in congestion. In Phoenix, drivers spend just 60% of their driving time in congestion. But with Phoenix being one of the fastest growing cities in the country, will adding more lanes help prevent future congestion?
What we generally think about when we're expanding freeways is the idea of adding capacity. Right after we add a lane to a freeway, what we generally see is that travel times are reduced and additional vehicles are accommodated on the road. However, over the long term, what that additional capacity tends to do is attract more drivers to the roads. So that capacity will ultimately end up getting filled and you're back to where you were before.
You probably have heard of something called Carmageddon, which was a major closure on a major stretch of the 405 freeway that took place over the entire weekend. And I guess after they added the lanes that they need to and restructured a portion of that particular freeway, I guess the time savings for some people wasn't really as much as the congestion and the headache and all that traffic had built during that Carmageddon time period.
Infrastructure are typically designed to last somewhere on the order of decades. We usually think about them lasting roughly 20, 30, 40 years. One of the challenges that we face right now is that a lot of our infrastructure across the US was designed and constructed roughly in the middle of the last century, roughly around 1940 through 1960. And a lot of that infrastructure has reached the end of its useful life. It doesn't mean that it's about to fall apart. What it means is that it's in need of major rehabilitation and maintenance.
One way LA is combating congestion and the cost of maintenance is with express lanes. In California, these are also known as H2B lanes. Their lanes are similar to high occupancy vehicle lanes, but LA drivers can only use them if they pay a fee.
So what you see here is on the right, you have vehicles that are going much more slowly on a freeway that the speed limit is probably 65 miles an hour. And on the left, you have pretty much free flow conditions. There's almost no congestion.
Paid express lanes are a new concept that has emerged in the past 10 years. The idea? Reduce congestion by encouraging carpooling or ride sharing. The fees can also create funds to pay for maintenance on the same corridors. Chester calls them an innovative strategy that many transit agencies are using.
I can certainly foresee a day when this same scheme is used in Phoenix.
some people feel that the people with money are able to basically bypass traffic. But the first freeway that they really started it on, which is the 110 freeway, it has been highly successful. They have expanded it to other freeways, and it has shown that it has not been as successful, and it could be the demographics of those who live in those neighborhoods and don't want to pay. And I think as long as there are still some free lanes for some people, I think that that will help both parties.
Traffic congestion and the high cost of road maintenance are two big issues facing many cities. But ASU transit engineers are tracking yet another infrastructure problem: extreme weather events.
We consider ourselves now living in the Anthropocene, which is the era of the planet that is largely dominated by human activity. When we can look at historical records of things like temperature or stream flow and say, how might these systems behave in the future? In the Anthropocene, what we expect is that these systems will no longer follow the patterns that we've experienced in the past.
As human activity continues to change and shape our planet, it creates challenges for engineers designing and planning our roads, buildings, water, and power systems.
So the challenges that we face in designing infrastructure in Phoenix are largely related to extreme temperatures, but we also have a flooding season, the monsoon season in the fall. So a lot of our infrastructure are designed for what we characterize as extreme events. When we design infrastructure to be able to withstand and continue performing under certain hazards like extreme heat or precipitation or flooding, what we typically do as engineers is decide how much hazard that infrastructure is going to be able to withstand. The challenge is that with climate change, infrastructure hazards are changing. So the infrastructure that we design may not be able to withstand these more frequent and more intense events.
Older established cities like LA and its suburbs are already seeing these issues.
I'd say I end up talking about weather affecting traffic, 50 to 60% of my weather forecast. What happens typically is that urban flooding. So you have these streets and freeways where the grates, they become covered with debris, and then often flooding happens, and then that water has nowhere to go. So it covers the entire freeway or the highway, and then cars can't go through there. Areas along our coast where we see homes, beautiful homes, being built right up there on the water, and you get big Pacific storms that roll on in here in Southern California, and they'll wash away the homes. They'll do tremendous amounts of damage as well as beach erosion.
But strong storms are not the only threat to infrastructure.
Once the wildfires happen, the vegetation is killed, it's demolished, the root systems are gone. We have had that lately, and you can see that in the Thomas fire. And unfortunately, up in Santa Barbara County, the Montecito area, they had tremendous amount of flooding. Then you have all that debris that flows into these catch basins. The catch basins aren't built to hold tons and tons of debris, and we lost a lot of property, we lost a lot of lives. And what happens is we're encroaching on areas where we really shouldn't be living.
How do we adapt to these new and rising issues without contributing to the problem? Green infrastructure may be part of the solution.
We solve that first mile, last mile problem by situations like this. We're here at Central and Roosevelt. We have a bike share station here. This would likely be somebody's last stop before heading to their apartment or their home. So we provide the bikes here to help them get that last mile to their apartment, to make it a little bit easier, a little bit better of an option than walking.
But encouraging people to use green infrastructure can be a challenge.
We really love our cars here in Arizona. We loved the convenience of them. It's hot a lot of the time. So just really convincing people that there is another option to driving your car, and it's a bike and it's fun, and you get to breathe in some fresh air and really enjoy the day on the bike as opposed to in the car.
Chester hopes that with more research and more green infrastructure, Phoenix can steer clear of LA's transit issues.
When we contrast Phoenix and Los Angeles, what we see is certain pieces of evidence that Phoenix is on the trajectory of Los Angeles, meaning that Phoenix, in some ways, may be building itself towards what Los Angeles experiences today. What we have going for us, one of many things, is that being a fairly new city, we have lots of examples from other cities of what could possibly go wrong in terms of, for example, financing infrastructure into the long term. So we have a lot of flexibility to be able to make changes based on what we've seen other cities experience. I'm hopeful that we will learn from the examples of many other cities in the U.S.
I'm Professor Vanessa Ruiz, and thank you for watching Catalyst, our show about shaping the future, how research creates real-life results. And because our lives have new problems that science can solve, we'll be back soon with more stories.
Catalyst is supported by Knowledge Enterprise Development at Arizona State University, advancing entrepreneurship, innovation, discovery, and knowledge for the public good.
Subscribe to this channel to see more episodes of Catalyst on YouTube.